So hey guys, welcome back to our advanced lecture. Today we're going to be talking about convex Hull trick. So basically the idea behind convex Hull trick is we want to maintain a set of lines in 2D space where we have the following two operations. So one is we want to be able to insert a line into the set. And for today we're going to be assuming that we insert the lines in non-decreasing slope order. So basically you have them in sorted slope order. You can have duplicate slopes, but you can't ever have them like decreasing essentially. And then the other operation we need is we want to be able to find the maximum y value for a given x value across all lines in the set. So I have a picture to kind of show what we're doing. So let's say these are the lines in the set at some point in time, right after we've done some amount of insertions. And then we can get some query for, say, this x value. And what we would return if we got this query is the point on this line at that x value, because at this x value, that is where your maximum value happens. And we could get a query over here, and then we would return this point on this line. And then if we're over here, we could get like a point on the green line. And what you can notice while looking at this is that your maximum value is always going to be on what kind of looks like a convex hull. So it like sort of looks like the bottom of a convex polygon, because you have like, in this case, these three segments form sort of your maximums over the whole range. And yeah, it has to be convex, because if you had like some concave angle like going up like this, then both of those lines would keep extending past that angle, and then they'd be like going above the maximum, which doesn't really make any sense. So you have to have this sort of convex hull shape on the bottom here. Yeah, so a couple of other observations we can make about this. Every line is either not on the hull at all, so it's either like not contributing anything to the maximums, like the blue line and the pink line, or it's the maximum for some interval. Right, so like if you have 2 points where a given line is the maximum, it has to be the maximum everywhere between those 2 points. And you'll have one line that sort of goes off to negative infinity, one line that goes off to infinity, but those are still intervals. And another thing is that your lines on the hull are going to be sorted in increasing slope order, right? So this line has some negative slope. Then this line has sort of a smaller positive slope, and then you go up to a bigger positive slope here. All right, so and any questions about this structure so far? Okay. So now the question is, how do we sort of represent this in such a way that we can maintain it in a nice way and do these queries? So first what we're going to do is we're going to make a struct. You could use a tuple for this. I'm only using a struct because it's slightly nicer to like get the individual elements out of it. But basically all that matters about this is that you have one double value and two integer values. So your three parameters for this struct are basically the starting x position of the segment, and then we're representing the line in like mx plus b format. So we have the slope and the y-intercept. So for example, like for the red line, its starting x value would be this point, because this is the first point where the red value gives the maximum. So we would store this as whatever this x value is, comma, whatever the slope intercept for the red one is. And for the green, we represent its start point as negative infinity. So we just have some really big negative number there that we know we'll never have to go past. And notice for this one, we don't have to worry about like storing it as infinity, because we're only storing the start point. So we just store whatever this point is, and then m and b. Okay, so that's how we're representing the individual segments on the hull. And then to represent the full hull, we just represent that as a vector of these segments in sorted order. So that's sorted order with respect to x and sorted order with respect to m. Because like we talked about before, if you have a bigger x value, then you have to have a bigger slope because the segments come in slope order. So that's a nice structure we can exploit. Okay.
Wait, sorry, I don't understand. Why do we need to sort by m if we're already sorting by x?
No. What I'm saying there is those two things are equivalent.
Okay.
Yeah. All right. Okay, so now how do we insert into the hull? So because we're inserting everything in sorted slope order, when we insert a line, we know that everything inside the hull has a slope that is not bigger than it, which means that this line is either going to not be on the hull, which is only possible if the line before it has the same slope and is like shifted higher up. We'll get into that case a little bit in a second. But then the other case is that it's the maximum value for all x bigger than some k, for some real value k, which means it's essentially the last line in the hull. So it's the one going off to infinity. So if it's not in the hull, we can obviously do nothing and just not insert it. Otherwise, we want to find the point k and sort of get rid of all the other lines that we have to make the hull still work. So we're going to go into the specific cases now, but this is just sort of a general outline for what we're going to do. Okay, so the first case is pretty simple. If the hull is empty, we want to just put the given line in at negative infinity and just return, right? Because if there's nothing in the hull, then this line just becomes the full hull. Otherwise, we want to look at the last line in the hull. So the one with the biggest slope and the biggest x value. So if the current line is bigger than the last line in the hull, so like in this case, what we want to do is we just completely get rid of this line. Because notice that this line is never going to be useful to us, because once we add this line here that's above it at this point, this line has a slope that is at least as big as this one. So the distance between these lines is, it could stay the same if they're parallel, but it could also just get bigger. There's no way this line will ever overtake this one. So we can just throw it out, essentially. And once we've thrown that out, we sort of continue again, because we're not sure what we should do with this line now. Or we're not sure if maybe we made the hull empty and we have to do the first case. But yeah, so in this case, we just take the last line off and we continue.
What do you mean greater? Sorry, I don't understand. What do you mean by greater?
So we're looking specifically at the start value of the last segment.
Right, but the value you're inserting now doesn't have a start value yet, right? You haven't given it a start value. So how are we comparing that?
Yeah, we're looking at that line's value at this x value. So like draw a line here.
Okay.
Which one's above?
Okay.
Yeah. Cool. Okay, so that's what happens if this one is above. Now we want to see what happens if the one currently in the hull is above. So there's two subcases for that. So one is the one we talked about before, where they're parallel. So if the one on the hull is above and they're parallel, then we want to just throw this guy out, because this line is always strictly better. Which, yeah, it's pretty self-explanatory. It's always going to be the same distance below that line in the hull. But then the other case is where this line has a bigger slope than this one. Remember, it can't have a smaller slope than that one because we do it in sorted order. So in this case, we can find an intersection point of these lines. And we know that that intersection point is going to be after this value where we checked it. So we're still checking here, and we see that the red line is below. But now we know that since this is a bigger slope, the red line has to eventually overtake it. So we can find that intersection point by basically just doing a little bit of algebra stuff. And then we find this point and we can insert the line into the hull with this starting point. And I had it on one of the previous slides, but I don't think I mentioned it. We have to have the starting x value as a double, because notice that even if all of your slopes and y-intercepts are integers, you can still have an intersection point that's at like some fractional x value. So we need to keep track of that, and the best way to do that is to just have it as a double.
In the first slide, you mentioned that we're sorting in by slopes, but on the previous slide where you kick off the parallel, right? What if the new guy has a higher y-intercept than your old guy? And shouldn't it be like you kick out the other guy?
Right, yes. Yeah, so then we are just in this case. Because this case, it doesn't matter if they're parallel or not.
Oh, okay. The 2 slides ago will take care of that thing. Okay, okay.
Yeah, yeah. So we're sort of going through these cases in order, I
Got you.
guess.
Okay,
Is
okay.
one way to think about it. Yeah. Okay. All right. Yeah, so these are basically the 4 cases we're handling. So the code for this basically looks like this. So if we want to insert a line with slope m, y-intercept b, we basically do this while loop, where we continuously look at the last guy in the hall. And if it has a bigger value than the line you're trying to insert, then that means we are in one of these 2 cases, right? Because these are the only 2 cases where the current back has a higher value than this given line. So for one of these 2 cases, what we want to do is first, if their slopes are not equal, then we know we're in the 4th case. So we find this intersection point, which is what I was talking about before, where like you do the equation of the line to find where they intersect. So this gives us the x value. And again, we want to cast to a double here. And then we just add back the current slope and y-intercept because we're adding the given line into the set. So this is one of 2 times that we'll actually add it into the set. And then once we're done with this, we just want to return. Because then we know we're done because we're in one of these 2 cases. We're in case 3 or case 4. And when we're in case 3, we want to just immediately return. And when we're in case 4, once we find this point and we insert this line, we're not going to continue because we don't need to know like what happens with this segment. We sort of found the stopping point, essentially. Okay, so that's what's going on in this loop. This is when the line in the hall is bigger than your line. So otherwise, if we escape this if statement, then that means that your line is at least as good as the one currently in the hall, which means that we can pop it off. So we can get rid of the last guy in the hall and then continue this loop. And then the only time we will exit this loop, other than this return statement here, is when the hull is empty. So when the hull.size is 0. And when that happens, this is going back to case 1 that we were talking about. We want to just insert the current line starting at -infinity, which we use as L long min here. Because usually you're not going to go lower than 10 to the minus 18. Okay, questions on this? Oh, and again, the s.m minus m is a trick I've used in I think a couple lectures before, but that's just checking s.m does not equal m. There's s.m minus m does not equal 0, basically. Okay. So the code for queries is a lot easier. So basically for a query, what we need to do is we need to find the last segment in the vector where its x value is at most the x value we want to query. Right, so yeah. So like if we're here, we want to look at the red line, right? Because if you have x values of -infinity, whatever this is, and whatever this is, the greatest x value less than the current x, this query here, is going to be here. So we want to find that segment in the vector. And the way we can do that is by using upper bound and then decrementing it. So we're using a custom comparator here. So what we could do is we could like make a segment struct. Actually, we haven't defined a comparator for segments, so we'd still have to do that. But basically, upper bound gives you the first element on the vector that is bigger than you. And that's according to this comparator we have here, which says that an x value is less than a segment if the x value is less than the x value of the segment. So we're basically just doing like a normal double comparison here, because again, the x value is a double. So that, yeah, that gives us the first segment with an x value bigger than us, and we want to sort of go back by 1. So we do the minus minus here, which takes you to the first segment, or the last segment with an x value that's at most the current x. And note that we don't have to be really careful about like the equals case, Because if there is a point, like an x value for a segment that's exactly equal to our query x, we can use either line because they'll be the same value there. So lower bound would work just as well here. So yeah, then once we have that segment, all we need is the value of that segment at position x. So we just return a y-intercept plus slope times x once we have this. Questions on this? On any of the implementation?
Wait, can you explain what upper bound does?
Yeah, so it's basically doing a binary search
Gotcha. Okay.
on your vector. And it looks complicated, but basically you can think about it as the binary search is only looking at the x values on the vector. Because we have it as a struct, so it has all these other values, but we're only looking at the x values.
I got
So
you.
yeah, you're just binary searching for the last x value smaller than you. And then once we have that, you just get the value at that point. Okay. Oh yeah, and this is another macro that we like to use, which basically just does hol.begin, comma hol.end, just to save characters. Okay. All right, anything else? All right. Okay, so now we're going to get into why this problem is useful. So a lot of times you'll run into DP solutions that look something like this, where it's like DP of I is the max over all j less than I of like some function of I times dpj plus some function of j. Or sort of like flip the dpj and the bj, it doesn't really matter. But just something like this where you have like, you want like the maximum of some linear thing with the smaller dp values. But it's not something that you can sort of immediately do, right? So you can always do like an n-squared solution for this, right? Because for every I, you can manually loop over all j and compute these. But what we can do in this case, when we have like this nice sort of linear structure, we can reduce that to n log n by representing it as inserting lines into a set. So basically, computing dpi is adding a line. And then, well, computing dpi is querying, and then we want to add it to the set for the future I.
Sorry, how is it querying if the line depends on AI?
Right, so what this is doing is this is querying at the x value AI.
Oh, that's cool.
Yeah, it's nice. Oh, wait, so one thing I forgot to go over quickly is the time complexity of all this. So queries are log n, right? Because you're doing the binary search on your segments. And the way we have them now, insertions are actually constant time amortized. Because notice that every time we run this while loop, we're popping something off of the vector. And we know that if we're inserting, say, n lines, we're only going to put at most n things into the vector. So the total complexity over all of our insertions is going to be O of n. So dividing that by n, we're getting on average constant time per insertion, which is nice. So yeah, insertions are constant time, queries are log time, which is why we can reduce this to n log n, because we're doing sort of n insertions and n queries. So the queries dominate, we get n log n complexity. Okay, yeah, so like I was talking about before, you can find DPI by sort of querying into the hull. Then you can insert that as a line so that you can compute DPI plus 1 with that. Okay, does that make sense? Okay, it'll probably make more sense once we get into problems. Yeah. Yeah, it's very nice. And a lot of these problems, it's sort of, they don't seem like convex hull problems at all. It's a lot like something like MaxFlow, where you have to like really hunt for it to like find it. But yeah, it's nice. Okay, so another thing is we can also use this to get min values. So up until now, we were just looking at max values. But if we want to change this to get min values, the code is almost exactly the same. It's literally like a 1 character difference. So the one thing we have to keep track of, though, is if we want to do a minimum haul, like we want to get minimum values, you want to have your lines inserted in descending slope order instead of ascending, right? So like if you look at what a minimum haul would look like, it's like the opposite of what we had before, where like you start off with a positive slope, then you go to like a small negative slope and then a bigger negative slope. So the lines are decreasing in slope this time. But it turns out if we want to change our code for this, all we have to do is change this greater than to a less than in the insert code, and everything else is the same. Okay. So one other quick thing to talk about is what do we do if the slopes are sorted in the wrong order? So the slopes are still in order, but they're not in the order we want, right? Like let's say we have a max haul and the lines are in decreasing slope order. So we can actually fix that just by exploiting this fact here, where we can sort of add a negative to both the slope and the x. So now if the slopes are descending, then the negatives of your slopes are going to be ascending. So if we insert with negative slopes and we query at the negative x values, we get the same answers. So you can sort of play with the negatives to make it work the way you want to do that. And I think you can also do a similar thing to turn a max haul into a min haul, but it's generally much easier to just change the one character. All right. Cool. Oh yeah, and one last thing is what's called the fully dynamic case, which is what if your lines are in like some random order? So this is much harder to solve. There's a couple ways you can do it. So one is you can do sort of what we did here, except have more complicated code that handles inserting a line sort of in the middle, which has a lot of edge cases. I've tried to do this a couple times, but it's just a complete mess. There's also something called a Lee Chow tree, which is basically like a specialized segment tree you can use for this, which in the Code Forces blog I saw about this. They really recommended doing this over trying to do something like this. But we're not going to worry about either of these cases for this lecture because there's still a lot of problems you can solve using the sorted slope case.
You can't like use a set or something where you just like insert in the middle, or is that the first case?
No, yeah, that's what this is, right? And I don't know, it's just it's very hard to figure out like which segments do you delete, like where do you add the intersection points? Like there's probably a nice way to reduce that to like not that much code. And I'm probably going to try to do that again at some point, but I'm not sure how hard that's going to be. But yeah, it's a lot less intuitive to deal with that. Okay. So now we can get into the problems. All right, so first problem is covered walkway. So you have to cover endpoints on a number line, and you can cover a segment from position x to y for cost c plus x minus y squared, where c is some constant that you're given. And you want to know what's the minimum cost you need to cover all the points. So in this case, let's say c is 8. This segment costs 8 to cover because you have x equals y equals 9. So that's just c plus 0, so that's 8. And this segment will cost 17 because you have 4 minus 1 squared, which is 9, plus 8. So this would be 17. And then your total answer is the sum of these two, which is 25. So yeah, so when you're thinking about these problems, it's usually helpful to first get the n squared dp, and then think about how you can sort of turn that into a convex hull trick situation. So I guess first, can you guys come up with the n squared dp? So again, it's not like sort of the usual n squared dp where you have like n squared dp states. We want to come up with something that has like n dp states where each one, like you do linear time to compute or something like that.
So at every point, you compute whether it's better to go across from. So for every point, for the points before that point, you want to compute whether it's best to skip over some of the points, and then whether, like, and then like do like do a linear time search throughout all the cases before that certain point. Something like
so by skip over, do you mean like cover them in the same thing?
Yeah, like 1, 2, 4, like skip over 3.
Yeah. Yeah. Okay. Well. Yeah, pretty much. So what you can do is like, for a given point, iterate over how many of the previous points you want to cover with your segment. Right. So like if you're at position 9, do we want to just do the 9, or do we want to do like a 9-4, or like a 9-4-2, or a 9-4-2-1? Right. So we have all those options of like how many we want to sort of skip over with the segment that covers 9. And then let's say we pick like 9-4. Then the answer for that would be whatever the cost of this segment is, plus whatever dp of 2 is, right? Because now we have to cover everything from 2 to the beginning. So what's like the cheapest way we can do that, basically? Yeah, okay, so that's the dp. So I think I put the dp on the same slide as the convex hull thing. Yeah, I can put it here, I guess.
You can like drag the window out of your like. Oh no, you're sharing the actual tab itself.
Yeah. No, I can do this. dpi equals min j less than I, and then this is something like c plus dp j minus 1. So let's say that j is the last guy that you want to put in your segment, right? So we want to compute it as something like this, where you take the min over j less than or equal to I of, first of all, that should be y, that should be xj, not yi. But yeah, we want to take the cost of the current segment plus dp of j minus 1, because we've covered everything up to j. So now we just have to go from j minus 1 forward. So can you guys see how to sort of manipulate this into a form we can use? Again, we need it to be like the equation of a line, basically.
You expand it out, the xy term or the ij term. I'm not sure how to deal with that. It's like it depends on both.
Right. Yeah. So I guess to think more about like what that ij term actually is, or yeah, because the ij term is actually fine, and it's kind of, the ij term is kind of the point, I guess, too.
Oh shoot! Oh yeah, you're right. Wait. Then the I squared term is the weird part one, right? I'm not sure.
Yeah, exactly. So how do you handle the I squared term? And also the c, right? Although I guess the c is fine. So, so it turns out,
does it appear all across all the points, and you can just subtract it out for the final answer, like add it onto the final answer.
yeah, pretty much. You can just like pull it out entirely because it doesn't depend on j at all. So yeah, so here's the DP solution we were just talking about, where again, DPI is the solution for the first I points. So we get this equation, and we can actually expand out this squared thing here, and pull out everything that doesn't have a j in it, right? Because the c plus xi squared is going to appear over everything. And then inside here, we have minus 2 xj times xi plus this function of j, right? So this is basically our y-intercept of the function, and then negative 2xj is the slope. So what we can do here is, again, it's like sort of the same strategy we were talking about before. We first compute DPI as c plus xi squared plus query xi, right? Because this we're querying at the x value xi with these slopes and intercepts. And then we insert a line that has slope negative 2xi plus 1 and intercept dpi plus xi plus 1 squared. And now when we compute dpi plus 1, we have all that already in the hull, so we can do the query. And you just sort of repeat, you like alternate queries and insertions like that until the end. And the other important thing to notice is that this is a min hull, and we do have the slopes in descending order, right? Because you have your x positions sorted in ascending order, so taking negative 2 times that is going to be descending. All right, questions on this? Okay, so the code for this, once you have the insert and query, is pretty straightforward. So it's basically what we were talking about with a couple edge cases to handle. So first of all, for the first point, you want to just insert that by itself, right? Because you only have sort of one option, right? Because if you're commuting DP of the first point, you know you have to just cover yourself. So we can do that insert without a query at all. And that way our hull is non-empty when we do the first query. And yeah, then for all of the other points, we compute DPI like we were talking about, and then we do the insertion. And then at the end, we just basically query DP n-1. And notice that we don't actually have to store the DP here because the hull is kind of doing that for us. So we can just have DPI be like an integer or something. We don't need like the full array. So yeah, does this make sense? Any questions on the code for this?
For like intermediate DP values, like past 1, like 2 or 3 or something, can't they also go all the way to 0? How do you account for that?
Oh yeah, that's what this is for actually. I think I said that wrong. I think this is not for the first point. I think this is sort of a dummy value for if you want to take everything. Right, because then this is doing the first n-1 points, and this is doing the last one. We're special casing the last one, not the first one. Yeah, that was my mistake.
Okay.
And yeah, that's another thing that's going to show up a lot here is sort of adding in a dummy case for taking everything. Okay. All right, so the next problem. So you're given n rectangles in the first quadrant that have one corner at the origin. And you know that no 2 of these rectangles are nested. So none of them are, there's no pair where one is inside the other. Every rectangle has some integer value ai, and you want to pick some subset of the rectangles such that the union of their areas minus the sum of their a values is maximal. So that's like a lot of conditions. We have an example for this. So let's say you have these 3 rectangles where like these are the y coordinates, these are the x coordinates, and these values inside the rectangles are their a values. So we have these 3 rectangles. Notice they all have a corner at the origin, and none of them are inside another one. Okay. And again, we want to maximize the area of the union minus the sum of the ai values of the ones we pick. So in this example, you want to take the first rectangle and the third rectangle because this gives you a value of So the area of the union is 1 times 9 for this rectangle, plus 3 times 10 for this rectangle. And then we subtract out the area they overlap, which is this rectangle here, which has an area of 3. So their total area of union is 9 plus 30 minus 3, so 36. And then we also have to subtract out their AI values. So we subtract out 1, we subtract out 2, and that gives us a total value of 33. So in this case, the answer would be 33. And the reason you don't want to take this middle guy is because if you take him, then you have to subtract 100 from your answer. And then it's going to be negative. Okay. Does the problem make sense?
Yep.
Okay. So again, first think about what's like an n squared dp you could do for this, and then we can break that down to n log n. So if you guys have any sort of observations for this problem too, go ahead, because there's a couple steps. Oh, yeah, there's a couple steps before we get to like the dp even. So even if you guys don't have an idea for the DP, how could you, I guess, sort of order them? And what would you define like the DP state to be? Even if you don't know how to compute it.
Like, so you have everything like the 3, 6, 9 thing, and then for like every like, so think of rectangles as like a checkerboard kind of, and then for every checkerboard you could either take entirely the left one, entirely the bottom one, either the union of the two or the entire thing.
So I guess think a little bit less complicated, because there's a simpler way you can state it, like based. Yeah, I don't know how to.
Maybe one sort of hint for how to think about the DP, right? Is that it's not the DP is slightly strange. It's not the DP of like the first N or anything, or first I or anything like that. There's an additional condition you want to think about. Maybe that'll help. That's a really bad explanation. I don't know.
Wait, it is the DP for like the first I, at least the way I have it.
Isn't there another? Do we need another thing? Like, do we need to take?
Oh, you take the ith guy?
Yeah.
Yes. Yeah. Okay. Yeah. Yes. So it is that. Yeah.
Yeah. I guess that's what it. So yeah, you think about not the first I, but also the first I, and you want to take the ith guy, and then how can you sort of, what ordering makes it nice?
Yeah. Exactly. So we want to have something like this, where like you sort the rectangles in order of increasing widths, and because they're not nested, then we know they're also in order of decreasing heights. Right, so as these rectangles get wider, they also get shorter. So now we can say define dpi to be the solution for the first I rectangles, given that you have to take rectangle I. So now, given that, how can we define dpi in terms of dpj for j less than I?
Hint, it's basically the exact same thing we did last time, like, which is, except the actual math is slightly different, but it's the same thing.
Yeah, it's very similar.
Yeah, so you want to like have DPI is equal to the maximum of dp of j minus 1. But then you have to do the math when you add dpj minus 1 and dp and the one you're at right now.
Yeah, exactly. So if we have, like, if we're given, say, dp0, and we want to, and we're looking at like dp2 right now. dp2 would be dp0 plus what, basically? Like, what do we, if we know we have to take number 2, and we're looking at number 0, and we want to take that as our next one. So we're not taking anything in the middle here. How do we compute dp2 in that case? And then again, we would iterate over all the rectangles less than 2, not just 0. But we're sort of iterating over what's the next guy you want to take.
Oh yeah, you have to do like math, like 2 and 0 compare against 2 and 1 and take the max of those two.
Yeah, exactly. So, but then the question is like, how exactly do you like extend, say, dp0 to include 2? And again, we're maximizing area of union minus sum of the AI. So what do we have to sort of add to dp0 to add in dp2, or to add in rectangle 2?
Oh, yeah, the area of 2, but then you subtract the area that they overlap.
Exactly, yeah. So we want to get rid of any of the area of 2 that's covered by any of your previous rectangles. And notice that this is going to be exactly the height of 2 times the width of your previous guy, because these rectangles are in order of decreasing heights. So the order of this rectangle's overlap with any of the rectangles past 0, or I guess 1 would be a better example. If we're looking at like 2 versus 1, the intersection of 2 with any of the rectangles 1 or below is just going to be the height of 2 times the width of 1. So that's the area we have to sort of subtract out from the whole area of 2. And then we also have to subtract that a2 because we want to subtract the a values. Okay. And it's, again, it turns out very similar to the last one. I think the math is even a little bit easier to turn it into convex hull trick. I think I'll just show you guys this one. So yeah, we want to compute dpi as the maximum for j less than I of the answer if we take I and then j and then some other stuff. So if we take ij and then some other stuff, then again, we take hi times wi minus wj, which is the area of rectangle I without all the overlapping area. And then we subtract out ai and we add in dpj. And we can sort of manipulate this and pull out all the terms that don't contain a j, and we get this form here, where you have hi times wi minus ai outside, and then it's actually a much nicer formula that we had last time inside here, because the intercept is just dpj, and the height and the slope is just wj. And notice that we have to sort of attach this negative here to the hi and not to the wj, because we need the slopes to be in ascending order for the max hull, and the wj are in ascending order. The widths are increasing as we go on. So yeah, that's just another thing to be careful about, is you have to get the slopes in the right order. All right, questions on this? And again, we need a special case if I is first, but we'll get into that with the code.
Oh yeah, because otherwise it'll be like 0 over 0, or right? If it's
yeah, I mean,
like if right? Am I thinking about that right?
there's something like that, yeah.
Or on some sort of undefined thing.
Yeah. Okay, so the way we can do that is insert 0, 0 initially, which is just inserting basically the x-axis as a line. And that turns out to handle the edge case where I is the first one you want to take. And then the one thing we have to be careful about here is we have to keep a running max of the DPI, because notice that DPI is the best answer where you take rectangle I. and we don't know which ones we want to take in our best answer. So we have to take the maximum over all the rectangles of the best one where you take this rectangle. And then, yeah, it's a very similar process to the last one, where first we calculate DPI using this query, and then we use DPI to insert another line that we can use to do the next few queries, to do all of your next queries until the end. And then once we've done all of those, we just print out the running max. Okay, questions on this? Cool. All right, so now we can get into our last problem. So in this problem, the statement is very complicated, but we'll do examples, we'll do all kinds of stuff. So you have n trees where each tree has a height and a cost. And you're given that the heights are strictly increasing and the costs are strictly decreasing. And also, you know that the first height is 0. No, the first height is 1 and the last cost is 0. So at every step, you can reduce the height of a tree by 1. And after you do this, you let B be the smallest cost value of a tree that you've fully cut down. Note that you always have to have one tree fully cut down, which means you have to begin by cutting down the first tree of height 1. And then, okay, so now you have this B value. Then you're going to pay B to charge your chainsaw up again, and then repeat. So then you decrease another tree's height by 1. And then you pay whatever the B value is now, and you repeat. And you want to know what's the smallest amount you need to pay to cut down all the trees. So there's a lot going on in this statement. We're going to go through an example. Okay, so let's say this is your initial setup, where your heights are 1, 2, 3, and your costs are 5, 4, 0. So notice that the heights are strictly increasing, and costs are strictly decreasing, and we have a height of 0 here, a height of 1 here, and a cost of 0 here. Okay, so like I said, in the first step, you have to cut down the first tree, which means we reduce its height to 0. And now if we look at B, which is, again, the smallest cost value out of all the trees that are fully cut down. So we only have 1 here. So B is 5, which means we now have to pay 5 to recharge the chainsaw. Okay, so now we want to go again. And it turns out in the optimal situation, we want to decrease the height of tree 3. Okay, we decrease the height of tree 3. B is still 5. We still only have 1 tree cut down. So now we have to pay another 5 to recharge. Then we want to cut down tree 3 again and pay another 5. So now our current cost is at 15. And now when we cut it down tree 3 for a third time, now its height is 0. So now B is 0, so we can recharge for free now. And you're always guaranteed that the last one is 0, as I've said a couple times. And so now that B is 0, it doesn't matter what we do. We can cut everything down for free. So then our final cost would be 15. Okay, anyone have questions about this example or how the problem works in general? There is a lot going on. Okay, so this is one where there's a lot of observations that go into it. So any, I guess, things you can say about like optimal strategy, or like what we want to do in general, anything like vague or yeah, just any observations, feel free to speak up.
You'll always want to cut down trees in descending order of cost until you hit 0, and then you do everything else, right?
Yeah, exactly. So the idea is, so the first thing is once you start cutting down a tree, you want to keep cutting it down until it's gone, right? Because you don't gain anything by like doing a tree partially and then doing something else and then coming back, right? Because that's just sort of wasting moves that you could be reducing your cost. And also, like Aki said, you want to cut down an increasing subsequence of trees. So that's like with respect to index until you cut down the last tree, at which point you can go back and cut everything else down for free. So like we did here in the last one, we cut down tree 1, then we cut down tree 2, and then we went back and we cut down tree 1, then we cut down tree 3, then we went back and we sort of did everything else. Because once you get this 0, it doesn't matter. You can do everything for free. So now all we need to do is find the cost of that optimal increasing subsequence. Because the cost of everything afterwards is 0. So given that we're sort of cutting down these trees in ascending index order, how do we turn that into a DP?
What do you mean by increasing?
So it's in order of increasing indices, and it's also in order of increasing heights. So like in this initial case,
I forgot.
yeah, we cut down first tree 1, then tree 3, which is, yeah, with respect to both indices and heights. But it's descending in terms of cost. Yeah, so the DP is going to be structured very similarly to the last two problems. This one comes out to probably the nicest DP state out of all the problems, which is weird because it's definitely like the ugliest statement and setup, but it reduces down very nicely. So one thing to think about is how many times are we sort of using every cost in the subsequence. So if your DP state is like DPI is the cheapest subsequence that ends at position I, like including I, how could you compute that from DPJ for j less than I? Because again, it's sort of the same structure as the other ones.
The max of the best previous one, so that would be stored in DP n-1, and then plus the index of the index, whatever that cost was, whatever the cost was at that index times the current height.
Yeah, you want to do that over all the indices, not just like I-1, but yeah, that's the right idea. So if for every tree that we cut down, let's say we cut down tree J, and then after that we cut down tree I. So we're going to pay a cost of BJ exactly AI times, right? Because we're going to use it once to cut down the last piece of tree J. Because after we cut down the last piece of tree J, we pay BJ to recharge. And then we're going to use it AI-1 times to cut down most of tree I. So everything except the last piece there. So in total, we're using BJ exactly AI times. Which means if we let DPI be the total cost for a subsequence ending at position I, that just turns into this, where DPI is min j less than I, BJ times AI, right? Because we have this cost here, plus DPJ. And notice that this is already like exactly the form we want. It's all very nice, like your slopes and intercepts are just like array values. And the slopes are decreasing, so we don't even need to mess around with negatives. So yeah, no need to rearrange anything in this case. Which means that the code for this is also incredibly short. You basically just do this. So we know that we always have to take the first tree, right? So we can insert the first tree like this. And then we never even have to like store an int value for DPI. We can just pass it directly into the insert function to insert it as the intercept for the line. So yeah, this will first calculate DPI using AI, then use DPI as the y-intercept for the line with slope BI, and then add that into the hull. And then at the end, we just need to know what's the cost to cut down the last tree. So we look at query A and -1. Questions on this problem? Okay. So yeah, thank you guys for coming. We have a bunch of problems and stuff on the next slide. We have some of the problems we did here, actually all the problems we had. And if you guys are interested in looking more into it, like the dynamic case or like a Lee Chow tree or something, these have information about that. So yeah, thank you guys for coming and hope to see you next week.